former Wharf station was built over water due to a lack of available space in the city center. Therefore, the two most critical construction techniques used were cofferdam and the top-down method. In this session, let's step into the shoes of the site engineers and follow the construction process in more detail. We need to construct the building both above and below this dock you see here. This building was originally designed to construct a station box over 300 meters long by reclaiming North Dock. However, considering cost and site conditions, we shortened the station box to 260 meters and chose to use a cofferdam instead of land reclamation. By constructing a cofferdam here, water is temporarily blocked to create a dry working space for construction. First, piles are driven into the ground. Since water tightness was crucial, we used 18-meter long tubular piles and installed a total of 310 of them. First, the piles need to be transported to the installation points above the water. They are loaded onto a large vessel called a barge. The barge's position is precisely controlled using GPS. The designed pile locations are converted into GPS coordinates and preloaded into the barge's system. Once the pile reaches its installation point, it is lifted vertically using a clamshell or hydraulic crane and inserted into the silent piler from Geekin, which is mounted on the barge. Before driving the piles into the ground, we used augering method for pre-boring, followed by hydraulic pressing to install them. Given the hardness of the ground at our site, augering was the most suitable drilling method. We first drive 2 or 3 piles into the ground with high precision. Then, the crane lifts the silent piler main unit and mounts it onto the installed piles. From this point, the silent piler switches to self-propelled mode and continues the work by moving on its own. Since the piles need to be installed in a U-shape, the piler has to turn corners. Even then, this machine automatically changes direction and moves on its own. As the piler drives the piles, interlock connections for water tightness are made immediately behind it. These connections link each pile to prevent water from entering the cofferdam. Additionally, to reinforce the watertight performance of the interlock joints, waterproof synthetic fiber sheets called geotextiles were inserted, and cement-based waterproof grout was injected into the gaps, completing a fully watertight cofferdam. This cofferdam had to withstand long-term loads as it was also used as permanent structure. Therefore, additional reinforced concrete piles were installed inside each hollow steel pipe pile to provide internal reinforcement. After driving the steel pipe piles to a depth of 18 meters, dry drilling was performed to install the RC piles, which were then inserted as concrete-filled piles down to 36 meters below the water surface. This graph shows that the filled piles have a greater resistance to bending moments compared to the hollow tubular piles. Since the internal reinforcement alone was insufficient to resist external lateral loads and water pressure, anchored piles were required. These piles, having the same specifications as the steel tubular piles, were additionally installed outside the cofferdam. At this time, the east and west anchor piles could not be arranged in a straight line because they were installed to avoid the TBM's path. The steel tubular piles needed to securely support the future construction of the sublevel 6th floor, so RC piles were inserted up to a depth of 36 meters below the water surface. And also, the anchor piles were reinforced with deep RC piles inside them. A total of 160 anchor piles were driven in at intervals of 2.92 meters. The installed anchor piles were connected to the cofferdam steel tubular piles with tie rods. This was to ensure that the cofferdam steel piles remained stable and did not tilt during construction. Considering when the water was pumped out, hydraulic jacks were used to apply a force of about 100 kN per meter to the tied walls, anticipating inward movement. As a result, initially, the walls were pushed outward, opposite to the excavation direction. But later, during dock dewatering, they moved toward the excavation direction. The construction site was adjacent to high-rise buildings, so any ground settlement was unacceptable. Therefore, inclinometers were installed, 21 on the geeken piles and 16 on the anchor piles, to monitor internal deflection and control tilting. In this way, the north, east, and west walls were completed. On the south side, since installing anchors in entire rows was impossible, the foundation of the existing building was used as a single wall to complete the four-sided enclosure. Now, it's time to pump out the water trapped inside the cofferdam. They used diesel-powered centrifugal pumps for dewatering, and the water was treated at an onshore purification plant installed in advance before being reused elsewhere. After dewatering created a dry environment, it was time to lower the equipment underground for the top-down construction. A sheet pile ramp was installed, allowing equipment to be moved toward the east in the direction of the Great Wharf Road Bridge. In addition to the existing southern wall of the previous building, which served as a barrier for dewatering, an additional southern wall, a second pile wall, was required for the construction of a Canal River station. First, pre-drilling is carried out using a continuous flight auger. Once the excavation is complete, second piles are installed. Unreinforced concrete soft piles are installed first to act as an initial earth retaining wall, followed by reinforced concrete hard piles between them to ensure structural strength. This second pile wall, constructed in this manner, supports the ground with its own rigidity, thereby securing structural stability. Now begins the full-scale implementation of the top-down construction method. Plunge columns are driven into the locations where the building's reinforced concrete columns will eventually be placed. These plunge columns temporarily support the load of the upper slabs during the top-down process. Due to the nature of the method, where slabs are constructed from the top-down downward while excavation process below, immediate structural support is required during each stage, and the plunge columns serve this critical role. A total of 30 plunge columns were installed on site, driven down to a depth of 14 meters below the surface along the building's center lines. The columns were not aligned in a perfectly straight line. At future more hole locations, 2 columns were placed side by side at 3-meter intervals. Once excavation is completed down to the lowest level and the permanent columns are installed, the structural role of these plunge columns is partially transferred. They are then integrated with the superstructure and used as part of the permanent structural system. Next is the slab construction phase. The first level to be constructed was the third basement level, or sublevel 3, which is the closest to the dock floor after water drainage. Excavation was carried out down to sublevel 3 to prepare for slab installation. The slab pouring began at the excavation lower level, and this slab is supported by the plunge columns. Slab construction was carried out in sections. The work was divided into 3 main parts, and each part was further divided into 3 sections, making a total of 9 construction sections. The reason for this division was the mole holes. After creating the upper slabs, mole holes were essential for lowering equipment and materials underground for excavation of the lower levels. There were 3 main openings, one on each side for escalator installation spaces, and one in the middle serving as a mole hole for workers and material movement. Because of these 3 large openings, slab construction was divided into 3 major parts. After construction, some mole holes were filled in, while others remained for vertical connections within the building, such as escalators, elevators, and the stairs on each floor. Due to the nature of the top-down construction method, the upper slabs are built first, followed by the lower slabs. At this stage, it was impossible for the plunge columns line to support the upper slabs, which span up to 30 meters in width. Therefore, additional support was required to provide basic connections between the plunge columns. For this purpose, the existing second pile wall and sheet pile wall on either side were utilized. During the construction of the sublevel 3 slab, the second pile wall was located below the slab level, naturally providing support at one edge of the slab. Support on the opposite edge was provided by the sheet pile wall. The slabs were connected to the kick and pile walls using a slab embedded into wall socket method. Pockets were curved into the kick and pile walls, and reinforcement structures capable of supporting the slab were first installed within these pockets. Following this, a structural system was formed between the second pile wall, planche columns, and kick and pile wall to support the slab. This setup allowed the upper slabs to be securely supported, enabling the safe continuation of construction on the lower levels. Excavation for the construction of lower slabs began around the mole holes. Soil was first removed through the mole holes, and the space was gradually expanded. Unlike at the sublevel 3, from the sublevel 4 downward, the slab-embedded wall socket method was applied not only to the kick and pile walls but also to the second pile walls, making it a necessary part of structural system. However, at locations where mole holes were present, the openings made it impossible to install foundational support structures such as beams, resulting in structurally vulnerable areas. Therefore, additional support was needed around the mole holes. In these cases, temporary columns were used to provide supplementary support during the construction process. Thanks to the top-down construction method, construction at Canary Wharf Station was able to proceed simultaneously on the sublevel 3, 4, and 6. After the sublevel 4 slab was completed, 3 activities took place concurrently. Foundation work on the sublevel 3 in preparation for the sublevel 2, installation of additional support walls and reinforcement of columns on sublevel 4, and excavation continuing down to sublevel 6. It is important to note that sublevel 6 was constructed before sublevel 5. Canary Wharf Station was a place through which the TBM had to pass for the line construction. Therefore, space had to be secured for it to pass. The subway runs at the lowest level of the station, sublevel 6, so the TBM also had to pass through sublevel 6. The diameter of the TBM used in the Crossrail project was 7.1 meters. If sublevel 5 was constructed first, the TBM would either have to break through that level while passing or might not be able to enter at all. Therefore, instead of building sublevel 5 first, sublevel 6 was constructed to secure space for the TBM. In fact, the floor-to-floor height difference between the sublevel 4 slab and sublevel 6 slab is 10.1 meters, and by removing sublevel 5 in between, a vertical clearance sufficient for the 7-meter TBM to pass was secured. The TBM was originally scheduled to arrive in the second half of 2012, so excavation down to sublevel 6 was completed by July 2011, and preparations to receive the TBM were finished by March 2012. By that time, construction of sublevel 2 and sublevel 1 had already been completed. However, due to unexpectedly harder ground conditions than designed, the TBM that started in May 2012 was delayed by about 7 to 8 months and finally reached Canary Wharf Station on May 31, 2013. Only after the TBM had passed was sublevel 5, the platform where passengers actually board and alight, constructed. After the completion of construction for the underground and above ground levels, a ventilation system and rooftop garden were installed. The ventilation system at Canary Wharf Station is crucial for its operation. Crossrail has installed platform edge doors to separate passengers from the trains and prevent debris from being sucked onto the tracks. These doors, however, create an almost airtight environment, causing a problem where trains traveling rapid through the tunnel push air forcefully ahead of them. This results in increased pressure within the station. To prevent damage to the platform doors, this pressure needs to be relieved. Therefore, a network of ventilation shafts not only extracts heat generated by braking, but also allows excess air to escape. 3 massive fans located at both ends of the platform help draw this air up to the surface. This process helps to relieve pressure and protect the platform during train arrivals. The most prominent architectural feature of Canary Wharf Station is its roof structure and rooftop garden. The Crossrail Place roof at Canary Wharf spans 310 meters in length, with each end cantilevering 13 meters over the surface of the North Dock. The roof construction of Canary Wharf Station involved the use of 1418 glue lamps and 564 steel connectors. Glue lamp, short for glue laminated timber, is a high-strength, durable material made by bonding multiple layers of dried lumber together with their grain aligned parallel. It is manufactured using water-resistant adhesives and compressed under high temperature and pressure using mechanical presses. At Canary Wharf Station, a total of 1418 glue lamp beams were used. Of these, only 4 beams, 2 at each end, are curved, while all the remaining beams are straight. This roof is constructed in a diagrid form. The term diagrid is a combination of diagonal and grid, describing a structural system that maximizes stability and load distribution through a network of diagonal lattice members. By distributing loads diagonally, the diagrid system can support the structure without relying on conventional vertical columns, enabling more open and flexible architectural designs. The roof structure was designed using parametric modeling, an algorithmic design approach that allows complex geometries to be created by controlling variables. As a result, the structure is asymmetrical, and nearly all components, including the glue lamp beams, steel connectors, and the ETFE panels above, were uniquely shaped with little to no repetition. Because of this complexity, detailed 3D prototyping was essential early in the design phase. Structural analysis was carried out using RFEM and RSTAB, allowing engineers to simulate the behavior of the roof and refine critical aspects such as geometry of the connection joints. The sizes of the members and nodes varied, so each component was assigned a serial number to allow for systematic comparison. A prefabrication approach was used, in which several units were assembled separately before being joined together on site. The total construction period for the roof took 7 months. Throughout this process, temporary steel frames were used to support the structure until each member was stabilized during assembly. At each node of the roof, the connection between the timber beams and ETFE panels was essential. An air pipe is installed between the timber beams and the ETFE, which plays a critical role in maintaining the consistent shape of the ETFE panels. By regulating the volume of air in response to varying wind pressure patterns, the system ensures that the ETFE retain its intended form as uniformly as possible. A garden was installed on the rooftop. To create this garden, plants had to be planted, which required soil with sufficient depth. As a result, the slab had to be thicker than those on other levels, inevitably leading to increased loads. However, at the eastern end of the structure, where the bridge passes, installing supporting columns was not feasible due to spatial constraints, and reinforced concrete alone could not provide sufficient support. As a result, this section was constructed using steel, which has higher tensile strength than reinforced concrete. Steel, while stronger in tension, is also more flexible. This posed a risk of deflection once the weight of soil and trees was added to the roof structure. To address this, a preload of 300 tons was applied to simulate the future weight of the garden. To achieve this, a temporary water pool was installed on the top of the structure to create the required load. This pre-stressing process allowed the structure to effectively respond to potential deflection once the soil and trees were added to the rooftop garden. To construct the rooftop garden, the drainage layer was installed first. At Canary Wharf Station, instead of using traditional drain boards, a lightweight porous drainage material was employed. This multifunctional material provides drainage, water retention, cushioning, and insulation, thereby enhancing both the efficiency and lightness of the rooftop garden structure. Following the installation of the drainage layer, a geotextile filter fabric was placed between the drainage layer and the soil layer to prevent soil erosion while maintaining drainage capability. For the planting layer, Lightweight soil was used instead of regular soil. This reduced the overall load on the roof structure while still supporting healthy plant growth. The rooftop garden at Canary Wharf Station, constructed in this way, is connected both to the underground subway station and the surface level. This allows easy access for passengers and pedestrians alike, making it an open public green space right in the heart of the city.